Welcome back to our podcast, where we explore the captivating world of data processing. Today, we're diving into batch processing, a foundational concept in data engineering that has seen significant evolution over the years. We'll discuss its development, the algorithms that drive it, and how it stacks up against other data processing methods like stream processing. So, whether you're just curious about data or you've been in the field for a while, put on your headphones. And let's jump in. To start, let's clarify what batch processing really is. Essentially, it involves gathering data over a certain period and processing it all at once. This method is particularly efficient when dealing with large volumes of data, but it does come with its own set of challenges, especially when it comes to optimizing queries and joins. One of the major advancements in batch processing has been the introduction of cost-based query optimizers, which you can find in frameworks like Hive, Spark, and Flink. These optimizers analyze the properties of the join inputs and automatically select the most appropriate join algorithms for the task at hand. This means, as a developer, you don't have to memorize all the different join algorithms. You simply declare the joins you need, and the optimizer handles the rest for you. This shift towards a more declarative approach marks a significant change from the traditional imperative programming style seen in systems like MapReduce. In MapReduce, you define functions, mappers, and reducers that process the data, but you have to manage the complexity of how those functions interact. While this flexibility allows for the use of a variety of libraries for tasks such as natural language processing and image analysis, it can also be quite cumbersome. Now let's discuss the benefits of incorporating more declarative features into batch processing systems. For instance, when it comes to simple filtering or field selection, a declarative approach can greatly reduce CPU overhead. Instead of calling a function for every single record, the query optimizer can read only the necessary columns from disk, which enhances performance. This is where frameworks like Hive and Spark data frames really shine, as they utilize vectorized execution techniques to optimize data processing. As we delve deeper into batch processing, it's interesting to note the rise of reusable implementations for common processing patterns. Historically, massively parallel processing, or MPP, databases primarily catered to business intelligence needs. However, that landscape is evolving. Today, batch processing systems are being applied across various domains, including machine learning and spatial analysis. Speaking of machine learning, frameworks like Mahout and Madlib are stepping up to provide reusable algorithms for tasks such as classification, recommendation systems, and even spatial algorithms like K-nearest neighbors. These tools are vital for similarity searches in multi-dimensional spaces, which are essential for applications ranging from recommendation engines to genome analysis. As batch processing systems continue to evolve, they are becoming more feature-rich and high-level, blurring the lines between them and MPP databases. Both types of systems fundamentally focus on storing and processing data, but their methods and capabilities are increasingly converging. Let's take a moment to unpack how batch processing actually works. In MapReduce, data is partitioned based on input file blocks. Mappers extract join keys, and the output is sorted and merged into reducer partitions. This step ensures that related data is grouped together, which is crucial for efficient processing. On the other hand, data flow engines have introduced their own innovations. They minimize the materialization of intermediate states, keeping more data in memory, which can speed up processing. However, this also means that if a node fails, they may need to recompute data. To address this, deterministic operators are employed to reduce the amount of data that needs to be recomputed, enhancing fault tolerance. When we think about join algorithms, they play a vital role in how data is processed in batch systems. Each input being joined goes through a mapper that extracts the join key. And then the reducer combines the records. If the inputs are partitioned correctly, this process can be further optimized using hash tables, allowing for efficient data lookups. And we can't overlook the importance of fault tolerance. In batch processing, the framework ensures that the final output remains consistent, even if some tasks fail and need to be retried. This reliability is crucial, especially when working with large datasets, as it allows for safe retries without compromising the integrity of the output. As we wrap up our discussion on batch processing, it's essential to highlight that this model is based on bounded input, meaning the data being processed has a known fixed size. Once all the input data is read, the job is complete. This stands in stark contrast to stream processing, which we'll dive into in our next episode. In stream processing, inputs are unbounded and jobs are never truly finished, as there's always more data flowing in. To conclude, batch processing is a powerful and evolving field that continues to adapt to the needs of modern data applications. With advancements in declarative programming, reusable algorithms, and robust fault tolerance mechanisms, batch processing systems are becoming more efficient and user-friendly. As we transition into the world of stream processing next time, we'll explore how these concepts change when dealing with continuous data flows. Thanks for tuning in, and we hope you'll join us for our next episode.